37 days. That's what remains between now, the 12th of November 2025, and December 19, when 3I, Atlas, will reach its closest point to Earth. 170 million miles will separate us, a distance vast enough to contain nearly 2 complete orbits of our planet around the Sun, yet closer than this ancient visitor will ever come again. After December 19, the gap will only widen, the geometry will only diverge, and within a handful of years, this object that traveled billions of miles and billions of years to pass through our neighborhood will fade beyond the reach of even our most powerful instruments, becoming once more what it was for almost all of its existence: invisible, unknowable, alone in the dark. This is not a close approach in the dramatic sense. There's no danger, no possibility of impact, no chance that 3I, Atlas, will swing near enough for us to see it with unaided eyes as a brilliant streak across the twilight sky. At 1.8 astronomical units, it will remain firmly beyond the orbit of Mars, well within the safe distances that separate celestial bodies in the vastness of space. But in astronomical terms, in the context of interstellar visitors that spend millions of years between star systems, this is intimate. This is as close as we get. The date itself, December 19, carries no cosmic significance. It's simply the point where the mathematical curves describing Earth's orbit and the comet's hyperbolic trajectory intersect most closely in three-dimensional space. Our planet moves along its familiar elliptical path at 30 kilometers per second, completing another lap in its 4.6 billion-year-long journey around the Sun. 3I, Atlas, cuts through that plane at an angle, racing outward at 58 kilometers per second after its gravitational acceleration near perihelion in late October. The geometry of those two paths creates a moment, a single instant in time, when the distance between the objects reaches its minimum before beginning to increase again, relentlessly, forever. Understanding that geometry requires thinking in 3 dimensions, not the flat sky we see when we look up at night. Earth orbits in a plane called the ecliptic, the same plane where most of the solar system's planets revolve. But 3I, Atlas, doesn't respect that arrangement. Its orbit is inclined at approximately 108 degrees relative to the ecliptic, meaning it's moving almost perpendicular to the planetary plane, cutting through our solar system at a steep angle. When we trace its path backward, before it entered our system, it was approaching from below the ecliptic plane. After passing perihelion, it's now climbing above that plane, heading northward in celestial coordinates as it races away from the Sun. On December 19, Earth and 3I, Atlas, will occupy positions in space such that a line drawn between them measures 1.8 AU. But they're not moving toward each other at that moment. By December 19, the comet will already be moving away from both the Sun and Earth, heading outward on its hyperbolic escape trajectory. Earth, meanwhile, continues its circular dance, orbiting a sun that the comet left behind weeks earlier. The closest approach is really a moment of convergence in the wake of the comet's perihelion passage, a brief geometric alignment that happens once and never repeats. For observers on Earth, this creates a specific viewing opportunity. In mid-December 2025, 3I Atlas will be located in the constellation Virgo, transitioning toward Leo as the month progresses. It will be visible in the pre-dawn sky for observers in the northern hemisphere, rising in the east several hours before sunrise. The moon will be in its waning crescent phase around December 19, meaning dark skies for most of the night, ideal conditions for detecting faint objects. The comet's brightness is predicted to be around magnitude 11 to 12, too faint for naked eye visibility but well within reach of amateur telescopes with apertures of 6 inches or larger. This matters because it democratizes the observation. Professional observatories with their massive mirrors and sophisticated instruments will conduct detailed studies, yes, but thousands of amateur astronomers around the world will also point their telescopes toward Virgo and capture their own images. Some will see nothing more than a faint smudge, a fuzzy patch barely distinguishable from background galaxies. Others, equipped with cameras and long exposures, will resolve the coma and possibly the ion tail that has been growing more prominent throughout November. A few, the most dedicated and skilled, might capture enough detail to contribute meaningfully to the scientific understanding of this object. The brightness of 11th or 12th magnitude places 3I Atlas at the edge of what's accessible to serious amateur equipment. For context, the faintest stars visible to the naked eye under perfect dark sky conditions are around magnitude 6. Each step in magnitude represents a brightness difference of about 2.5 times, so a magnitude 11 object is roughly 100 times fainter than what the unaided human eye can detect. This is where telescopes become essential, gathering light across mirrors or lenses large enough to boost faint signals above the detection threshold. But the comet is fading. Throughout November, as it moves farther from the Sun, the rate of sublimation from its nucleus declines. Less ice turns to gas. Fewer molecules escape into space. The coma, that glowing envelope of gas and dust surrounding the solid core, gradually shrinks. The ion tail, so prominent in early November observations, will likely persist through December, but will grow fainter and harder to detect as the solar wind's interaction with the diminishing coma weakens. By January 2026, the comet might drop below magnitude 12, then 13, then 14, each step making it harder to observe, requiring larger telescopes and longer exposures to capture any signal at all. This decline is predictable, governed by the physics of how ice responds to temperature. The farther a comet travels from the Sun, the less energy hits its surface. Sublimation rates drop exponentially with distance. Water ice, which becomes active around 3 AU from the Sun, will largely cease outgassing by the time 3I Atlas crosses 4 or 5 AU in early 2026. Carbon dioxide, more volatile than water, will persist slightly longer, but even CO2 ice stops sublimating efficiently beyond a certain distance. What we're witnessing now, in November, and will witness in December, is the active phase of this comet, the brief window when solar heating drives vigorous outgassing. After that, 3I Atlas returns to dormancy, becoming a dark, inert lump of ice and rock coasting silently through space. The December 19 flyby represents more than just a geometric milestone. It's the culmination of a 5-month observation campaign that began with the comet's discovery on the 1st of July 2025. Since that first detection by the Atlas Survey telescope in Chile, astronomers have been tracking this object continuously, gathering data from dozens of facilities, building a dataset that captures how an interstellar comet behaves as it passes through our solar system. Discovery, characterization, perihelion passage, post-perihelion evolution, and now the final close approach before departure. Each phase has provided unique data, answering some questions while raising others. What makes the December observations particularly valuable is that they represent our last chance to study the comet under favorable conditions. After the Earth flyby, the distance will increase rapidly. By January 2026, 3I Atlas will be more than 2.5 AU from Earth. By March, when it passes Jupiter's orbit, it will be over 4 AU away. The brightness will have dropped so much that only the largest professional telescopes will be able to detect it at all, and even then, detailed spectroscopy or resolved imaging will become impossible. The data gathered in December, during this final window of relative proximity, might be the last detailed observations humanity ever makes of this particular object. And it is this particular object, this specific lump of ice and rock with its unique history and composition, that we'll be losing. 3I. Atlas is not interchangeable with other comets, not replaceable. It carries chemistry from a star system that might no longer exist, having formed billions of years ago when the universe was younger and the Milky Way had a different structure. The molecules locked in its ice represent conditions that prevailed in some distant region of the galaxy during an epoch we can only study indirectly through ancient light and theoretical models. When 3I Atlas departs, it takes that information with it, back into the interstellar void where it will remain inaccessible until, perhaps millions of years from now, it passes near another star and another civilization has the chance to observe it. 37 days. Astronomical timescales usually dwarf human experience, stretching across millions or billions of years, rendering individual human lifetimes irrelevant. But here, in this moment, the timeline compresses to something we can grasp. 5 weeks. Just over a month. a span of time short enough that we can count it in days, mark it on calendars, plan our observations, and arrange our schedules around it. It's a reminder that while the universe operates on scales almost incomprehensible to mortal beings, occasionally those scales intersect with our own, creating moments of convergence where cosmic events and human timekeeping align. On the night of the 19th of December 2025, somewhere on Earth, a telescope will capture the last high-quality image of 3I Atlas at its closest approach. The observer won't know, in that moment, that it's the last good image. The comet will still be visible for weeks afterward, still technically observable. But that December 19 observation, whenever and wherever it occurs, will represent the peak of our final encounter. After that, it's all distance and fading and eventual silence. This is the nature of interstellar visitors. They arrive unannounced, pass through quickly by cosmic standards, though months pass by our reckoning, and then leave forever. No return visits, no second chances. We get one flyby, one observation window, one opportunity to ask our questions and gather our data. And then they're gone, and we're left with whatever we managed to learn, whatever images and spectra and measurements we captured during that brief window of visibility. 37 days from now, the window begins to close. The final approach begins its transition to final departure. And those of us watching, whether through professional telescopes or amateur equipment or simply through the images shared online, will be witnesses to a farewell that is both ending and beginning. Ending for us, as this visitor fades from our view and our reach. Beginning for the comet, as it returns to the interstellar journey that was interrupted for a few brief months by our sun's gravity. It came from the darkness, passed through our light, and will return to darkness. And we were here to see it. The observation campaign for December 2025 represents one of the most coordinated efforts in the study of interstellar objects, and the stakes couldn't be clearer. Every telescope matters, every spectrum captured adds to our understanding, every image contributes to the final portrait of an object we'll never see again. The Hubble Space Telescope has already scheduled multiple observation windows around the December 19 closest approach. Hubble observed 3I Atlas once before, back on the 21st of July 2025, when the comet was 277 million miles from Earth, still inbound toward perihelion. Those images showed a teardrop-shaped coma with a reddish color indicative of organic compounds and dust. They provided an upper limit on the nucleus size of approximately 5.6 kilometers, though uncertainty remains because distinguishing the solid core from the surrounding gas and dust envelope is extraordinarily difficult, even with Hubble's resolution. The December observations aim to answer a question that has persisted since discovery. Has the nucleus fragmented? Comets are fragile objects, loosely bound aggregations of ice and rock held together by weak gravity and the structural strength of frozen materials. When they approach the Sun, thermal stress can cause them to crack and split. We've seen this happen to solar system comets many times. Comet Shoemaker-Levy 9 famously broke into more than 20 fragments before crashing into Jupiter in 1994. Comet Ison disintegrated as it grazed the Sun in 2013. Even relatively robust comets like 67P, Churyumov-Gerasimenko, studied up close by the Rosetta spacecraft, show fractures and evidence of previous splitting events. 3I Atlas endured significant stress during its October 30 perihelion passage. At 1.4 AU from the Sun, temperatures on the sunlit side of the nucleus would have exceeded 200 degrees Celsius. The night side remained frozen near absolute zero. This temperature gradient creates mechanical stress. Ice sublimating on one side produces thrust, torquing the nucleus and potentially causing it to spin faster. If the object was already fractured, if pre-existing cracks ran through its structure, the perihelion passage might have widened those cracks into complete separation. Avi Loeb, the Harvard astrophysicist, who has been vocal about considering unconventional explanations for interstellar objects, published analysis suggesting that if 3I Atlas is a natural comet, it should have experienced significant mass loss at perihelion, possibly even fragmentation. His November observations showed a compact source without clear evidence of breakup, but the resolution was limited by ground-based telescopes observing through Earth's atmosphere. Hubble, above that atmosphere, can do better. If the nucleus has split into multiple pieces, Hubble should be able to resolve them as distinct points of light separated by measurable distances. Why does this matter? Because fragmentation tells us about the object's structural strength and composition. A rubble pile, a loosely bound collection of smaller pieces held together by weak gravity, fragments easily. A monolithic body, a single solid mass of ice and rock, is more resistant. If 3I Atlas survives perihelion intact, it suggests either that the object is structurally robust or that it experienced less thermal stress than models predicted, perhaps because its composition is unusual, rich in volatiles that absorb heat through sublimation rather than allowing temperatures to rise high enough to cause mechanical failure. The James Webb Space Telescope will focus on spectroscopy, using its infrared instruments to dissect the light coming from the comet into its component wavelengths. Webb observed 3I Atlas once before, on the 6th of August 2025, using the near-infrared spectrograph to capture detailed data on the molecules being released from the nucleus. That August observation detected carbon dioxide, water vapor, carbon monoxide, and carbonyl sulfide, providing the first detailed chemical inventory of this interstellar visitor. The December observations will repeat those measurements to track how the chemistry changes as the comet moves farther from the Sun and cools. Is the relative abundance of different molecules shifting? Are we seeing deeper layers of the nucleus exposed as the surface erodes? Water ice and carbon dioxide ice don't necessarily mix uniformly in a comet. They can form layers, with more volatile species concentrated in certain regions and less volatile materials elsewhere. As the comet loses mass, we might be looking at different layers, different epochs of its formation history, each with slightly different chemical signatures. Isotopic ratios are particularly important. Hydrogen comes in two stable isotopes, normal hydrogen with 1 proton and no neutrons, and deuterium with 1 proton and 1 neutron. The ratio of deuterium to hydrogen in water varies depending on where and when the water formed. Water that condensed in the cold, outer regions of a protoplanetary disk tends to have a higher deuterium to hydrogen ratio than water that formed closer to the star. By measuring this ratio in 3I Atlas, astronomers can infer something about the temperature conditions in the disk where this comet originated. Similarly, carbon comes in two stable isotopes, carbon 1,2 and carbon 1,3. The ratio between them carries information about the chemical processes that created the carbon-bearing molecules in the comet. Oxygen has 3 stable isotopes, sulfur has 4. Each ratio is a clue, a constraint on the models, a data point that helps narrow down where in the galaxy and under what conditions this object formed. Webb is uniquely suited for this work because its infrared instruments can detect wavelengths that are absorbed by Earth's atmosphere. Ground-based telescopes, no matter how large, cannot observe certain molecular transitions because the light never reaches the surface. Space telescopes bypass that limitation. Webb's sensitivity allows it to detect molecules present in trace amounts, species that make up less than 1% of the outgassing, but which might be diagnostically important. On the ground, observatories across the world are coordinating their efforts. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, the Gemini telescopes in both hemispheres, all are planning observations around the December timeframe. These facilities use adaptive optics systems that measure atmospheric turbulence in real time and adjust the shape of their mirrors thousands of times per second to compensate, achieving resolutions that approach the theoretical limit imposed by the size of their mirrors rather than being blurred by atmospheric distortion. Spectroscopy from these ground-based giants complements the Space Telescope observations. They can capture visible and near-infrared light, tracking emission lines from ions in the coma, measuring the velocity of gas expanding away from the nucleus, searching for rare molecules that might only be detectable during brief flares or outbursts. They also provide temporal coverage. Space telescopes like Hubble and Webb have limited observing time, allocated across hundreds of different projects. They can't stare at 3I Atlas continuously. Ground-based observatories fill the gaps, maintaining surveillance, watching for changes, ensuring that if something unexpected happens, we capture it. And then there are the amateur astronomers, The network of thousands of individuals scattered across every continent except Antarctica, equipped with telescopes ranging from modest 6-inch reflectors to sophisticated instruments rivaling small professional facilities. This distributed network has become essential to modern astronomy. Amateurs discover supernovae, track asteroid positions, monitor variable stars, and yes, observe comets. For 3I, Atlas, amateur contributions are particularly valuable because of the global distribution. Professional observatories are concentrated in specific locations chosen for their excellent atmospheric conditions and dark skies. Chile, Hawaii, the Canary Islands, Australia, but those locations don't provide continuous coverage of the entire sky. An object rising in the evening for observers in Chile is setting in the morning for those in Australia. A comet visible from Hawaii might be below the horizon for European observers. Amateur astronomers fill these gaps, providing 24-hour coverage, ensuring that if the comet undergoes a sudden brightening, a fragmentation event, or any other transient phenomenon, someone somewhere will be watching. The data collection strategy is comprehensive. Imaging to track the comet's size and morphology, spectroscopy to measure composition and isotopic ratios, photometry to monitor brightness changes that might indicate rotation, outbursts, or fragmentation, polarimetry to study how light scatters off dust grains, revealing information about particle size and composition, radio observations to search for complex molecules that emit at microwave wavelengths. Every technique, every wavelength, every data type adds to the picture. Radio telescopes are conducting searches for organic molecules. The Atacama Large Millimeter Array in Chile, a collection of 66 radio dishes working together as a single instrument, can detect the faint emission from molecules like formaldehyde, methanol, and ethanol. These molecules are fragile, easily destroyed by ultraviolet radiation, so their presence indicates they're being continuously produced or are protected within the coma. Finding amino acids, the building blocks of proteins, would be extraordinary, though the abundances are probably too low for current instruments to detect. Even if complex organics aren't found, the absence of certain molecules is informative. Science proceeds by ruling out possibilities as much as by confirming them. If we don't detect methanol despite having the sensitivity to do so, that tells us something about the chemical environment where 3I, Atlas, formed. If certain isotopic ratios differ from solar system comets, that constrains models of stellar disk chemistry in other systems, every measurement, positive or negative, refines our understanding. The December observations will be archived, stored in databases maintained by space agencies and astronomical organizations, accessible to researchers for decades to come. Future scientists, equipped with analysis techniques we haven't invented yet, will return to this data, extracting insights that current methods might miss. The data from the Hubble observation of comet Hale-Bopp in 1997 is still being analyzed today, nearly 30 years later, yielding new discoveries as computational methods improve and theoretical understanding deepens. This is one of the beautiful aspects of astronomy. The data is permanent. Once captured, it remains available for reanalysis forever. The photons that left 3I, Atlas, on December 19, 2025, traveled across 170 million miles of space, passed through telescope optics, struck detector arrays, and became numbers in a file. Those numbers will outlive the people who observed them, outlive the telescopes that captured them, outlive possibly the institutions that funded them. They become part of humanity's permanent record of the universe, a legacy passed forward to future generations who will ask questions we can't yet formulate and find answers we can't yet imagine. But to create that legacy, the observations must happen. December 2025 is the window. After that, the comet fades, the distance grows, and the opportunity closes. This is why every telescope matters, why the coordination is so extensive, why professional and amateur astronomers alike are preparing for this final observation campaign. We get one chance, this is it. And in 37 days, that chance arrives. On the 19th of December 2025, somewhere on Earth, someone will be looking at a computer screen showing the latest image of 3I, Atlas. They'll see the faint smudge of the coma, perhaps the ion tail stretching away from the sun, maybe even resolve the nucleus as a point of light distinct from the surrounding glow. They'll run their analysis, extract their measurements, add their data to the growing archive. And they'll know, whether consciously acknowledging it or simply feeling it as a vague awareness, that they're participating in humanity's farewell to this visitor, capturing the last detailed portrait before it slips away into silence. The data will tell us what we managed to learn, but it will also tell us what we didn't learn, what questions remain unanswered, what mysteries persist. And those unanswered questions will guide the design of future missions, shape the capabilities of next-generation telescopes, inform the strategies for observing the next interstellar visitor whenever it arrives. This is how knowledge accumulates, how science progresses, through incremental steps where each observation builds on the previous ones, where every encounter with the unknown teaches us how to do better next time. December 2025. The final observation campaign. 1 month to gather everything we can, to ask every question we can formulate, to capture every photon we can detect. And then, in January, the long goodbye begins. After December, the story of 3I Atlas transitions from observation to projection, from data collection to extrapolation. The comet will continue moving, of course, following the trajectory carved by gravity and momentum, but our ability to watch that journey fades with distance until we're left with mathematics, with orbital equations predicting where the object will be, even though no telescope can confirm it. By January 2026, just weeks after the closest approach to Earth, 3I Atlas will have receded beyond 2 astronomical units from our planet. The brightness will drop below magnitude 13, then 14, pushing the comet toward the threshold of detectability for all but the largest telescopes. The ion tail, so prominent in November observations, will likely have dissipated by then, the activity level having declined to the point where insufficient gas escapes to sustain visible ionization. What remains will be the faint glow of the coma, itself shrinking as sublimation rates fall with increasing distance from the Sun. March 2026 marks another geometric milestone, though one we'll likely observe only indirectly if at all. That's when 3I Atlas crosses Jupiter's orbital distance, passing through the realm of the gas giants approximately 5.2 astronomical units from the Sun. Jupiter itself won't be anywhere near the comet during this crossing. The giant planet follows its own 12-year orbit around the Sun, and the alignment that would place Jupiter and 3I Atlas in proximity simply doesn't occur in this passage. But crossing Jupiter's orbital distance signifies entering the outer solar system, the region where water ice remains permanently frozen and where comets from our own Oort cloud spend most of their time in dormancy between their rare ventures toward the Sun. By March 2026, 3I Atlas will be approximately 6 AU from Earth, too faint for amateur observation and challenging even for professional facilities. Any remaining observations will be sparse, opportunistic, captures when larger telescopes have gaps in their schedules and can spare a few minutes to check whether the comet is still detectable. The data from these late observations will be minimal, probably just astrometric positions confirming the predicted trajectory, showing that the comet is where mathematics says it should be. This gradual fade into undetectability is the fate of all interstellar visitors. Oumuamua, discovered in October 2017, was last observed in January 2018, just 3 months after discovery. By then it had faded to magnitude 27, detectable only by pointing the Hubble Space Telescope at precisely the right coordinates for long exposures. After that, silence. The object continues to exist, continues to move, currently somewhere beyond Saturn's orbit heading outward, but no instrument can see it anymore. It's lost to observation, though not to calculation. We know where it is, approximately, but we can't confirm it. 2I, Borisov, discovered in August 2019, remained. Visible longer because it was more active, producing a substantial coma and tail that scattered sunlight efficiently. Observations continued through October 2020, more than a year after discovery, but eventually it too faded beyond detection, disappearing into the dark sometime in late 2020 or early 2021. Again, we know its trajectory, can calculate its position for centuries into the future, but we can't see it anymore. 3I Atlas will follow this pattern. The last professional observation will probably occur sometime in mid-2026, roughly a year after discovery. After that, the comet will drop below magnitude 24 or 25, becoming too faint even for the most sensitive instruments operating at the longest exposure times practical for tracking moving objects. There might be one final attempt in late 2026 or early 2027, a last-ditch effort to capture it before it's truly gone, but by then the signal-to-noise ratio will be so poor that extracting useful data becomes impossible. And then, officially, observation ends. The object will be logged in databases with a note indicating the date of last detection, marked as no longer observable, classified as a lost object that continues to exist somewhere out there, but beyond our ability to track. The trajectory prediction will remain, a mathematical abstraction describing where the comet should be if our understanding of its velocity and the gravitational forces acting upon it is correct. But without observational confirmation, we can't know for certain. The trajectory itself is well constrained by the months of observations between July 2025 and early 2026. Dozens of observatories captured hundreds or thousands of images, measuring the comet's position against background stars with precision. Those measurements fed into orbital determination software that calculated the 6 parameters describing the comet's path through three-dimensional space: position, velocity, and orientation. The solution is robust, the uncertainties small enough that we can predict where 3I Atlas will be decades from now with reasonable accuracy. By 2030, 5 years from now, the comet will be approximately 30 astronomical units from the Sun, somewhere in the region between Neptune and the Kuiper Belt. It will be traveling at roughly 58 kilometers per second relative to the Sun, having slowed slightly as it climbed out of the Sun's gravity well, but still moving fast enough to escape entirely. At that distance, solar heating is negligible. Surface temperatures will have dropped to around 40 Kelvin, cold enough that all volatile ices have ceased sublimating. The comet is dormant again, a dark, frozen nucleus coasting through space, indistinguishable from the countless other small bodies that populate the outer reaches of our solar system, except for its velocity, its hyperbolic trajectory that marks it as an outsider. By 2050, 25 years from now, 3I Atlas will be beyond 100 AU, more than 3 times the distance to Neptune, approaching the heliopause. The heliopause is the boundary where the solar wind, that stream of charged particles flowing outward from the Sun at supersonic speeds, meets the interstellar medium and slows to subsonic velocities. It's not a sharp boundary, but rather a transition region, tens of astronomical units thick, marking the edge of the Sun's influence, the frontier between our solar system and interstellar space. The Voyager 1 spacecraft crossed the heliopause in August 2012 at a distance of approximately 122 AU from the Sun, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November 2018 at 119 AU. Both spacecraft continue to send back data, measuring the properties of the interstellar medium directly for the first time, revealing that the space between stars is not empty but filled with a tenuous plasma, remnants of ancient supernovae and stellar winds from billions of stars, all mixed together in a medium that permeates the galaxy. 3I Atlas will cross that same boundary sometime around 2050, though the exact date depends on the variable position of the heliopause, which shifts inward and outward in response to the Sun's 11-year activity cycle. Unlike Voyager, the comet carries no instruments, transmits no data, marks its passage with no signal we can detect. It simply continues, moving from the Sun's domain back into the realm from which it came. By 2100, 75 years from now, the comet will be several hundred astronomical units from the Sun, well into interstellar space, traveling through the local interstellar cloud, that particular region of the galaxy where our Sun happens to be located. At that distance, the Sun will appear as nothing more than a bright star among countless others, no longer the dominant gravitational influence, no longer the source of heat or light sufficient to affect the comet's frozen surface. 3I Atlas will have fully returned to the interstellar environment, indistinguishable from any other small icy body drifting through the darkness between stars. The timescales stretch out. 1,000 years from now, in the year 3025, the comet will be thousands of AU away, farther than the Oort cloud, that spherical shell of comets surrounding our solar system at distances up to 100,000 AU. The Sun will have faded to just another star, no brighter than many others in the sky, and 3I Atlas will be a silent wanderer in the true interstellar medium, moving through the spiral arm of the galaxy at 58 kilometers per second relative to the frame of reference it briefly passed through. 10,000 years from now, in the year 12025, the comet will have traveled approximately 18 light-years from the Sun, assuming constant velocity and no significant perturbations from other stars. It might be approaching another stellar system, or it might be in the empty space between systems, drifting through a region that won't see a close stellar encounter for millions of years. We have no way to know. The galaxy contains approximately 200 to 400 billion stars, but the average distance between them is several light-years, and most of space is empty. The probability of 3I Atlas colliding with anything, with a planet or moon or even another comet, is vanishingly small over human timescales. Space is so vast, and solid objects so rare relative to that vastness, that collisions are extraordinary events. The comet will likely spend millions or tens of millions of years in transit between star systems, passing through the interstellar void without encountering anything more substantial than individual gas molecules and dust grains. But eventually, statistically, it will pass near another star. The timescale might be 1,000,000 years or 10 million or 100 million. The encounter might be close, within a few AU, or it might be distant, a passage through the outer reaches of another star's gravitational influence without ever venturing close enough for significant heating. If the encounter is close enough, if the geometry is favorable, the comet might be captured into an orbit around that star, becoming a permanent resident of a new system, no longer interstellar, but once again a member of a stellar family. Or it might pass through, as it passed through our system, gravity bending its trajectory slightly but not enough to capture it, sending it onward toward the next encounter and the one after that, potentially continuing for billions of years, crossing the galaxy multiple times, witnessing the birth and death of stars, surviving in the frozen dark long after the Sun has exhausted its fuel and swelled into a red giant, long after Earth has been consumed or ejected, long after every trace of our civilization has vanished. This is the scale of time that comets inhabit. They exist on geological timescales, galactic timescales, timescales where a human lifetime is a fleeting instant and recorded history is barely a moment. 3I Atlas is billions of years old, has survived since before our solar system existed, and barring some catastrophic collision, will continue to exist for billions more. It will outlive stars. It will outlive galaxies in their current configurations. It will persist as long as the matter itself persists, as long as ice remains frozen and rock remains solid, as long as the universe permits the existence of small, cold, dark objects drifting through the void. And we got to see it. For a few months in 2025 and early 2026, this ancient, enduring traveler passed through our neighborhood, briefly illuminated by our sun, briefly observable by our telescopes, briefly within reach of our instruments and our curiosity. We captured images, we measured spectra, we calculated trajectories, we asked questions, and we received answers, incomplete though they may be. Now it departs. After December 19, after the closest approach, the distance increases day by day, kilometer by kilometer, until the comet fades. Beyond detection, and then beyond prediction, and finally beyond memory, except as data in archives, as papers in journals, as a footnote in the history of astronomy noting that in 2025, humanity observed its third confirmed interstellar object and learned from it what we could before it slipped away. The galaxy is full of such objects, billions upon billions of them, drifting between the stars, carrying their ancient chemistry, their silent histories, their frozen records of worlds and epochs long gone. Most will never pass through any solar system. Most will never be observed by anyone or anything. They'll simply exist, traveling through the dark, obeying gravity and inertia, enduring for eons without witness or purpose or meaning beyond the simple fact of their existence. But occasionally, one passes through. Occasionally, the geometry aligns, and when it does, we watch, we learn what we can, and then we let it go, back into the darkness, back into the silence, back into the vast cold night from which it briefly emerged. There's something profound about knowing that this is temporary, that this intersection of trajectories is a moment that will not repeat. We live most of our lives surrounded by permanence, or at least the illusion of it. The sun rises every morning, the moon cycles through its phases every month. The stars wheel overhead in patterns our ancestors recognized thousands of years ago. Even our most distant spacecraft, Voyager 1 and 2, remain in communication, still sending back data 48 years after launch, still reachable, still part of our extended presence in space. But 3I, Atlas, is different. It arrived without announcement, without invitation, without any connection to our history or our plans. It came from a place we've never seen, formed in conditions we can only infer, traveled for a duration that renders human timescales irrelevant. And now, after a brief passage through our sunlight, it returns to that same unknowable realm, departing not to some location we might someday reach, but to a trajectory that will carry it beyond our civilization's entire future span, beyond the lifetime of our species, beyond the habitable period of our planet. This impermanence forces a kind of urgency that's rare in astronomy. Most of what we study in the universe will still be there tomorrow, next year, next century. Galaxies don't disappear overnight. Stars evolve slowly by human standards, taking millions or billions of years to progress through their life cycles. Even relatively dynamic phenomena like supernovae leave behind remnants that persist for thousands of years. We can plan observations carefully, build instruments over decades, wait for the perfect conditions because we know the targets will remain available. Interstellar visitors don't offer that luxury. They arrive and depart on timescales measured in months or a few years at most. Miss the observation window and it's gone forever. This creates pressure, yes, but it also creates focus. Every telescope, every observing hour, every data point becomes precious because we know the opportunity is finite. And that focus, that concentration of effort and attention, often leads to insights that might not emerge from more leisurely studies of permanent objects. What have we learned from 3I Atlas? The chemistry, certainly. The detection of carbon dioxide, water, carbon monoxide, and carbonyl sulfide provides a chemical profile different from the average solar system comet, suggesting formation in a colder or more distant stellar environment. The high CO2 to water ratio points toward conditions where carbon dioxide could condense more efficiently than it does in our own system's comet-forming regions. These observations constrain models of how protoplanetary disks evolve chemically at different distances from their stars, adding data points from a system we can never visit. The age estimate, 3 to 11 billion years, places this object among the oldest we've ever studied directly. Most solar system comets formed 4.6 billion years ago, along with the Sun and planets. Objects from that epoch carry chemistry from the molecular cloud that collapsed to form our system. But 3I Atlas might predate that collapse by billions of years. If the older age estimates are correct, this comet formed when the universe was less than 3 billion years old, in the early generations of planetary systems when the galaxy had a different chemical composition, fewer heavy elements, a different stellar population. The survival of such an object across that timescale tells us something about the durability of ice in interstellar space. Cosmic rays, ultraviolet light from stars, occasional close passages to other stellar systems, all exert erosive pressure on interstellar comets. The fact that 3I Atlas still retained sufficient volatiles to show activity at perihelion suggests either that it's quite large, with a thick protective mantle insulating the interior, or that the interstellar environment is less destructive than some models predict, allowing ice to survive for billions of years with relatively modest erosion. The velocity, 58 kilometers per second relative to the Sun, fits within the expected distribution for objects orbiting the galaxy, but is notably higher than the previous two interstellar visitors. This might simply be statistical variation, 3 data points being far too few to characterize a population, or it might indicate something about where in the galaxy 3I Atlas originated. Objects from the inner galaxy, closer to the galactic center, tend to have higher orbital velocities than objects from the outer regions. If this comet came from a denser stellar environment, it might have received velocity kicks during close encounters that wouldn't occur in sparser regions. The missing or weak dust tail, much discussed in November observations, might ultimately be explained by a low dust-to-gas ratio or unusually large dust grains that don't respond efficiently to radiation pressure. This would tell us something about how dust aggregated in the comet's formation environment, whether the disk had different properties that inhibited fine dust production, or whether the comet represents a particular subset of the population that happens to be dust poor. But beyond these specific scientific findings, 3I, Atlas, has taught us something more general about our place in the galaxy. We used to think of the solar system as isolated, a small island of matter orbiting one star among billions, separated from other systems by gulfs of empty space so vast that meaningful interaction was impossible. The discovery of interstellar objects has changed that picture. The space between stars isn't a void, but a medium populated with debris from countless other systems, objects ejected during planetary formation or perturbed out of their orbits by gravitational interactions, now wandering the galaxy on independent trajectories. The detection rate, approximately 1 confirmed interstellar object per year with current survey capabilities, implies that millions or billions of such objects pass through the inner solar system over the Sun's lifetime, most too small or arriving from directions that make detection unlikely. We're not isolated. We're immersed in a galaxy-scale ecology where matter circulates between systems, where the remnants of one star's planetary formation become visitors to another system billions of years later, where chemistry and perhaps even the ingredients for life can be transported across interstellar distances, not through deliberate mechanisms, but through simple orbital dynamics and chance. This realization has implications for how we think about the origin of life. Panspermia, the hypothesis that life or its precursors can spread between worlds, becomes more plausible when we understand that interstellar transport of complex organic molecules happens naturally through objects like 3I, Atlas. The comet carries carbon, compounds, water, organics formed in its parent disk. If it were to collide with a young planet with suitable conditions, it would deliver that chemistry intact, seeding the planet with materials that took millions of years to produce through disk chemistry, but which arrive suddenly in a single impact event. We're also learning about the statistics of planetary system formation. Every interstellar comet is an experiment conducted by the galaxy, a test of whether certain chemical compositions and structural properties allow objects to survive ejection and interstellar travel. The diversity we're seeing among the 3 known objects suggests that planetary formation produces a wide variety of outcomes. Not all systems make comets like ours, not all disks have the same chemistry or dynamics. The galaxy is running billions of these experiments simultaneously, and occasionally we get to observe one of the results. Future observations will build on what we've learned. The Vera C. Rubin Observatory, beginning full operations in 2025, will discover many more interstellar objects over the next decade, potentially 1 or 2 per year initially, increasing as the survey deepens and algorithms improve at distinguishing interstellar trajectories from solar system orbits. Each new discovery will add to the sample size, allowing statistical analysis that's impossible with just 3 objects. We'll be able to characterize the population, measure size distributions, chemical diversity, velocity distributions, understand what's typical and what's rare. ESA's Comet Interceptor mission, launching in 2029, waits in orbit for a suitable target, ready to deploy a probe that can fly past and study a pristine comet up close. If an interstellar object is discovered with favorable geometry and sufficient lead time, Comet Interceptor could become humanity's first mission to an interstellar visitor, capturing images and measurements at distances of hundreds or thousands of kilometers, rather than hundreds of millions. That would be transformative, revealing surface details, composition, structure at resolutions impossible from Earth. But even without interception missions, even with just remote observations, we're entering an era where interstellar objects transition from rare curiosities to regular occurrences, from anomalies that generate headlines to expected discoveries that contribute to ongoing research programs. This normalization doesn't diminish their importance. Each one remains a unique sample from another system, a data point from a region of the galaxy we can't reach any other way. But it does change how we approach them, allowing more systematic study, better planning, more comprehensive observation campaigns. And perhaps someday, centuries or millennia from now, when humanity has spread beyond Earth and developed technologies we can't yet imagine, we might build spacecraft capable of catching up to interstellar visitors, matching their velocities, traveling alongside them, studying them at leisure rather than racing against observation windows measured in months. We might even retrieve samples, bring pieces of these ancient travelers back to laboratories where we can analyze them with techniques far more sophisticated than remote spectroscopy. We might drill into their nuclei, extract ice cores, read the layered history of their formation the way we read Earth's climate history in Antarctic ice. But that's speculation, wishful thinking about futures that may never arrive. What we have is now, December 2025, 37 days until the closest approach, and then the gradual fade into silence as distance and diminishing activity render the comet unobservable, returning it to the darkness from which it briefly emerged. There's a melancholy to this, a sense of loss that's unusual in science. We're accustomed to studying objects that remain available for future generations to revisit with better instruments and deeper understanding. But interstellar visitors are finite experiences. The observations we make now are all we'll ever have. Future astronomers won't be able to check our measurements by re-observing the same object. They'll have to trust our data, our calibrations, our analysis, or repeat the study with different objects and hope the results generalize. This finality makes the December observations feel weighted with responsibility. We're not just gathering data for ourselves, for papers we'll publish next year or the year after. We're gathering data for everyone who comes after, for researchers who aren't born yet, for questions that haven't been formulated, for insights that require context we can't yet provide. The data we capture in December will be consulted in 2050, in 2100, in 2200, assuming our civilization and its archives persist, becoming part of the permanent record of how the universe works and what we learned from this particular messenger that passed through our corner of it. And maybe, just maybe, somewhere in the data, there's something we're missing, some pattern or anomaly or correlation that won't become apparent until we have dozens or hundreds of interstellar objects to compare. Maybe the unusual chemistry of 3I, Atlas, its high carbon dioxide abundance or its peculiar dust-to-gas ratio, will turn out to be characteristic of objects from a particular galactic region, a signature that helps us map the chemical gradients across the Milky Way. Maybe its velocity will fit into a pattern that reveals something about how gravitational interactions in dense stellar environments differ from the dispersed regions where our Sun orbits. We can't know what future insights await because we can't predict what questions will be important decades or centuries from now. But we can collect the data, preserve it carefully, document it thoroughly, and trust that someone, sometime, will find value in the photons we captured during these brief months when 3I, Atlas, passed through our sunlight. On the 19th of December 2025, the distance reaches its minimum. After that, it's all expansion, all separation, all gradual fade, and eventual silence. The comet will continue its journey, carrying its ancient chemistry back into interstellar space, moving at 58 kilometers per second toward whatever encounters await in the millions of years ahead. It doesn't know we observed it. It doesn't care. It simply moves, obeying gravity and momentum, existing because matter exists, and enduring because the universe permits frozen ice to persist in the dark. But we know. We watched, we measured, we wondered, and in that wondering, in that brief attempt to understand a visitor from beyond our world, we participated in something larger than ourselves, something that connects us to the galaxy and to timescales that dwarf human history. We stood on a small planet orbiting an ordinary star and looked up at a piece of another world passing through, and we asked questions and sought answers and learned what we could before it slipped away. That's what we do. That's what consciousness permits and curiosity demands. We observe the universe, we try to understand it, we preserve what we learn for those who follow. And sometimes, In moments like this, when an ancient traveler passes through our light, we're reminded that we're part of something vast and old and ongoing, a story written in matter and motion across billions of years and billions of light years, a story that includes us not as central characters but as witnesses, observers, curious beings who happened to be here when the stranger arrived and who took the time to look up and say hello and goodbye in the same breath. Sleep well, knowing that above you, beyond the atmosphere, beyond the moon, beyond Mars, an ancient comet is racing outward, carrying chemistry from a star system that might no longer exist, traveling toward encounters we'll never witness in times we'll never see, and knowing too that we were here for this moment, this brief convergence, this fleeting intersection of one visitor's billion-year journey with the few thousand years of human curiosity about the night sky. 37 days until December 19, and then the long goodbye begins,